Today we're going to set up some applications of calculus by talking about what's called implicit differentiation, which is really just a fancy way to say we're going to use the chain rule on steroids. But maybe a better way to define implicit differentiation is we are going to take the derivative of an equation, which is interesting because up till this point we've taken the derivatives of functions where we only have one side of the equal sign to work on. This time we're going to have both sides of the equation. And this equation is going to be in x and y, or it might have several variables, assuming y is a function of x, whose derivative then is dy dx, the derivative of y with respect to x. So, for example, if I just wanted to take the derivative of y, the derivative of y is 1, because the derivative of a variable is 1, but remember we have to use the chain rule and multiply by the derivative of the guts. The derivative of y is dy dx. So we're treating y like it's this mysterious function. In other words, if we want to take the derivative of maybe y squared, we can take the derivative of the outside, which is 2y, times the derivative of the guts. And the derivative of y is dy dx. Now I want to notice this is different than what we saw before with the partial derivatives, where we took the derivative in the x direction or the y direction. Here what we're doing is we're treating y as a dependent variable on x. In other words, y is an equation that has x in it. Last unit, when we did implicit differentiation, x and y were both independent of each other. X could be whatever it wants, and y could be whatever it wants. Here, x and y are connected by an equation, so there is a dependent relationship. That is different than implicit differentiation. Also, as a note, along the way as we do this, we will have to do some work to actually solve for the dy dx, or solve for the derivative. And that may involve factoring the dy dx factor from several terms. So if we end up with multiple dy dx's we're solving for, we may have to get everything with the dy dx on one side, everything without it on the other side, so that we can factor it out and divide by the remaining factor. So that's pretty much the idea here. Let's do several examples, and I'm going to do a lot of examples today. I'm going to do 7 different examples, and if you feel like you've got this concept down, what's happening, feel free to stop the video after I write a problem up. See if you can do it yourself before I work it out, and see if we agree or disagree on the answer. If you feel like you're doing really, really good on this, you can even jump from the video to the homework a bit early. But all 7 of these examples are going to really focus on this same concept. So here's the first example that we're going to look at. The first example is 3xy plus 4y squared equals 10. So this is an equation that connects x and y. They are dependent on each other. So when we take the derivative of both sides, first with the 3x, we have to treat this now as a product. 3x times y. So we take the derivative of the first, which is 3, times the second, y, plus the derivative of the second, and the derivative of y is dy dx. times the first, 3x. So that's the product rule. We've done the derivative of the first times the second, plus the derivative of the second times the first, remembering that y is a function with x, so the derivative of y is dy dx. Plus the derivative of 4y squared is 8y to the first, times the derivative of the guts. Whenever we take a derivative of y, we need a dy dx term. Equals the derivative of 10, that's a constant, is 0. Now we're going to solve the remaining equation for the dy dx. To do that, we need to get all the terms with dy dx on one side, and everything that doesn't have a dy dx, specifically that 3y, on the other side. So I'll subtract the 3y from both sides. And that's going to give me, putting the 3x in front, 3x dy dx, plus 8y dy dx equals negative 3y. Now once we have all the dy dx's on one side and everything else on the other side, we can factor out the GCF of dy dx times what's left is 3x plus 8y, and that equals negative 3y. Pretty simple from here. We divide both sides by that factor, and dy dx is equal to negative 3y over the 3x plus 8, and we have our derivative taken implicitly. So that's this idea of implicit differentiation. We treat the y like it's a function of x, and take the derivative, like always, but whenever we have a derivative with y, we have to multiply by the derivative of the guts, which is dy dx. And then we solve for that dy dx. So let's try another example. Let's do x plus the square root of x times the square root of y equals y squared. And remember, we think about square roots as 1/2 powers. So first, the derivative of x, delete that. First, delete that. First, the derivative of x is 1, plus, again, you'll notice we have a product. So we use the product rule. The derivative of the first is 1/2 x to the negative 1/2 times the second, which is y to the 1/2, plus the derivative of the second, which is 1/2 y to the negative 1/2 times the first. Also notice, though, we took the derivative of a y, so we have to multiply by a dy dx here, times the first, which is x to the 1/2. So again, being able to see the product rule here, it's the derivative of the first times the second, plus the derivative of the second times the first. Also noticing that when we took the derivative of the y, we had to multiply by dy dx at that point. Continuing on the other side of the equation then, because we have to do the same thing to both sides of the equation, the derivative of y squared is 2y, and because there's a y in that derivative, we multiply by dy dx. Now, this one might need some cleanup, so let's do 1 plus the negative exponent moves x to the 1/2 to the denominator. Y to the 1/2 stays on top. Plus the negative exponent moves the y to the 1/2 to the denominator with the 2. The x to the 1/2 is in the numerator. Dy dx equals 2y dy dx. Now we want to probably get rid of the fractions. The fractions are going to make this ugly and a pain to work with. So we'll multiply by the common denominator of 2x to the 1/2, y to the 1/2 on every term. So it's 2x to the 1/2, y to the 1/2. 2x to the 1/2, y to the 1/2. 2x to the 1/2, y to the 1/2. And 2x to the 1/2, y to the 1/2. And when we do, we have 2x to the 1/2, y to the 1/2, plus the 2's divide out and the x's divide out. So we have y to the 1/2 plus 1/2 is just y, plus the 2's divide out and the y's to the 1/2 divide out. And we have x to the 1/2 plus 1/2, which is just x to the first, dy dx, equals 2 times 2 is 4, x to the 1/2, y to the 1 plus 1/2, which is 3/2, times dy dx. That was a d up there. So now let's get the terms with the dy dx on one side. We can do that by subtracting the x dy dx from both sides. And that gives us x to the 1/2, y to the 1/2, plus y equals 4x to the 1/2, y to the 3/2, dy dx minus x dy dx. It's ugly, but that's okay. Never said calculus was pretty. What we're really interested in is that everything on the left has a dy dx that we can factor out. And that leaves behind 4x to the 1/2, y to the 3/2, minus x. The left side's still the same, x to the 1/2, y to the 1/2, plus y. And so if we divide each side by that denominator, we have, let's do a different color, dy dx is equal to x to the 1/2, y to the 1/2, y plus y, all over 4 x to the 1/2, y to the 3/2, minus x. And we have our solution. A lot of algebra to get there, but the idea is the same. We're getting all the dy dx's on one side. Factor out the dy dx so that you can isolate it. We don't care how ugly it gets along the way. It's the same strategy and the same process. So if we have an equation to do like x cubed plus y cubed equals 9xy, we should be able to take the implicit derivative. The derivative of x cubed, 3x squared, plus the derivative of y cubed is 3y squared, times the derivative of y, which is dy dx, is equal to, we've got a product, 9x times y. Be careful of these products. The derivative of 9x is 9 times the second, plus the derivative of the second, which is 1, dy dx, times the first, 9x. Not much cleanup to do, so let's get all the terms with dy dx on the same side, everything else on the other side. And then we can go two directions here. They're both basically the same. Let's keep the 3x squared positive just for kicks. So I'm going to subtract 3y squared dy dx from both sides. So moving all the dy dx's to the right. Everything without a dy dx, that's the 9y, needs to move to the left. And so we have 3x squared minus 9y equals 9x dy dx minus 3y squared dy dx. Again, we've got this factor of dy dx on the left side. I'm sorry, that's the right. That we can factor out dy dx, and that leaves behind 9x minus 3y squared. The other side still 3x squared minus 9y. And so if we divide both sides by that 9x minus 3y squared, we have 3x squared minus 9y over 9x minus 3y squared is equal to dy dx. Always check to see if you can factor and reduce, though. You might notice everything's divisible by 3. Delete that. Dividing everything by 3, we've got 3 times x squared minus 3y over 3 times 3x minus y squared equals dy dx. And then we can reduce out those 3's. So we have our final answer. The derivative of y with respect to x is x squared minus 3y over 3x minus y squared. Let's try some more interesting problems. How about we do x squared e to the y plus y equals x cubed. Very common to have products as we work with this implicit differentiation. Again, we've got a product x squared times e to the y. So the derivative of the first is 2x times e to the y, plus the derivative of the second, e to the y. The derivative is e to the y times dy dx. Whenever we take the derivative of y, we have to multiply by dy dx times the first, which is x squared. Don't forget any pieces. You should be able to look at it and see the derivative of the first times the second, plus the derivative of the second times the first. 4 parts to that derivative. Plus the derivative of y, we know, is just dy dx equals the derivative of x cubed is 3x squared. Now we want to get all the dy dx's on one side, everything else on the other side. So we will subtract the 2x e to the y from both sides. And that gives us e to the y x squared dy dx plus dy dx equals 3x squared minus 2x e to the y. And now that that dy dx is on the same side, we can factor it out, leaving behind e to the y x squared plus, don't forget, plus what? Anything divided by itself is 1. It does not disappear. Equals 3x squared minus 2x e to the y. And so one final step is to divide by that factor. So we have dy dx is equal to 3x squared minus 2x e to the y all over e to the y x squared plus 1. We have our derivative. Let's try one with a log in it. Let's try number 5. Y natural log of x plus 2 equals e to the 3/2 power y. Oops, how about this? Let's do x to the 3/2 power y to the 5/2 power. Taking the derivative of both sides, we again have a product, y times the natural log of x. So the derivative of y is dy dx times the second, natural log of x, plus the derivative of natural log of x is 1 over x times the first, which is y. The derivative of 2 is nothing. Equals, we have another product. So the derivative of the first is 3/2 x to the 1/2 times the second, y to the 5/2, plus the derivative of the second, which is 5/2 y to the 3/2. Since there's a y, we have to do dy dx times the first, which is x to the 3/2. My 5 disappeared. There we go. So, not much cleanup to do. We do have a dy dx on the left and a dy dx on the right. So let's get those all on the same side. Doesn't really matter which side. So let's move all the dy dx's to the right. Doesn't really matter, but I'm going right. Dy dx, natural log, subtract that from both sides. Then we'll subtract anything without a dy dx off the right side. So we'll subtract 3/2 x to the 1/2 y to the 5/2 from both sides. So those are gone and those are gone, and we have 1/2. We have 1 over x times y, that's y over x, minus 3/2 x to the 1/2 y to the 5/2 equals 5/2. Let's put the x first, x to the 3/2 y to the 3/2 dy dx, minus, we'll put the natural log x first, dy dx. I want to clean up the fractions first. I really don't like fractions. Let's multiply both sides of the equation by the denominator 2x. Each term by 2x. So the x's are gone, and we have 2y minus, the 2's are gone, 3 1/2 plus 1 is x to the 3/2, y to the 5/2 equals, the 2's are gone, so we've got 5x to the 3 plus 1, or 3/2 plus 1, which is 5/2, y to the 3/2, dy dx, minus 2x natural log of x dy dx. Now that we took care of the fractions, we're back into the dy dx business. They're all on one side, so let's factor it out. Dy dx times 5x to the 5/2 y to the 3/2 minus 2x natural log of x. Other side is still the same, 2y minus 3x to the 3/2 y to the 5/2, and we finish it up by dividing both sides by that factor, so we know that dy dx is equal to this lovely fraction, 2y minus 3x to the 3/2 y to the 5/2 all over 5x to the 5/2 y to the 3/2 minus 2x natural log of x. What a beautiful solution. Don't get lost in the algebra. It's the same process we've always been doing. Taking the derivative, we just know that y is now a function of x, so we have to multiply by dy dx. And then solve for dy dx. And solving is pretty much always the same. Get all the dy dx's on one side, everything else on the other side. So let's do another example. Let's do 2x e to the xy equals e to the x cubed plus y e to the x squared. Oh, I didn't number this one. Whoops. This is number 5. So, We got a lot of stuff going on here. Good derivatives here. We've got a product. So the derivative of the product on the left side is the derivative of the first, which is 2, times the second, e to the xy, plus the derivative of the second. The second is e to the xy times the derivative of the guts. And you might notice that the guts is a product, xy. So we've got to treat it like a product, which we do the derivative of the first, which is 1, times the second, y, plus the derivative of the second, there's our dy dx, times the first, which is x. So we've got the product. Oh, then we have to multiply by the first part, 2x. Always helps after a product rule, make sure it's all there. Derivative of the first times the second, plus the derivative of the second times the first. By the way, the derivative of the second included a product, derivative of the first times the second, remember the first was just 1, times the derivative of the second times the first. Make sure you're not missing any parts as you review and take a look at the problem. That's just the left side. We move to the right side. The right side of e to the x cubed is e to the x cubed times the derivative of the guts, which is 3x squared. Plus, we have another product. The derivative of the first, the derivative of y is dy dx, times the second, e to the x squared, plus the derivative of the second, that's e to the x squared, times the derivative of the guts, which is 2x, times the first, which is y. A brief check to make sure we didn't forget anything on that product. We've got the derivative of the first times the second, plus the derivative of the second times the first. Should be really good at product rule by the end of this lesson. Need to clean this up. Let's see, on the right side, we're going to distribute everything through those parentheses. So we have 2e to the xy plus, and I want to notice we've got a 2x and an e to the xy that have to distribute in. So that's 2xy e to the xy plus 2x squared e to the xy dy dx. Then on the right side, we've got 3x squared e to the x cubed plus e to the x squared dy dx plus 2xy e to the x squared. Again, now that we've taken the derivative, we need to get all the dy dx's on the same side. I think I labeled this as number 5. I just realized we already have a 5. This is number 6. I'm having a problem numbering. Sorry about that. Anyways, doesn't change it. We've got all these dy dx's. We have to get them on one side. Get everything else on the other side. So our dy dx's are here and here. Doesn't really matter which direction we go. Let's move them to the right this time. So we'll subtract e to the x squared dy dx from both sides. E to the x squared dy dx from both sides. So those are gone. We got to get everything without a dy dx then over to the right. So we'll subtract 2 e to the xy. So subtract 2 e to the xy. Subtract 2xy e to the xy. Subtract 2xy e to the xy. And we now have 2x squared e to the xy dy dx minus e to the x squared dy dx equals 3x squared e to the x cubed plus 2xy e to the x squared minus 2e to the xy minus 2xy e to the xy. It's big, it's ugly, and it doesn't matter because the process is still the same simple pattern. Factor out that dy dx. Gives us 2x squared e to the xy minus e to the x squared equals 3x squared e to the x cubed plus 2xy e to the x squared minus 2e to the xy minus 2xy e to the xy. And divide to get dy dx alone, and it's just the ugly fraction 3x squared e to the x cubed plus 2xy e to the x squared minus 2e to the xy minus 2xy e to the xy all over 2x squared e to the xy minus e to the x squared. And we have our implicit derivative. The algebra might be a little work to crank out, but the process is the same. Take the derivative implicitly, so the derivative of y is dy dx. Get all the dy dx's on one side. Get everything else on the other side so that you can factor out the dy dx and divide. One last example. The natural log of x squared plus y squared equals the natural log of 5x plus y over x minus 2. Taking the derivative of the left side. On the left side, the natural log is 1 over x squared plus y squared times the derivative of the guts. The derivative of x squared is 2x plus the derivative of y squared is 2y dy dx equals the derivative of the natural log of 5x is 1 over 5x times the derivative of the guts, which is 5, plus y over x. We can either treat it as a quotient or as a product y times x to the negative 1. We've done a lot of products today, so I'm going to keep this as a quotient. So we have low d high, the derivative of the top is 1 dy dx, minus high y d low, the derivative of x is 1, all over, we square the bottom, and away we go. Let's see. We've got some denominators. We've got x squared plus y squared, that's a factor. The 5's divide out, which is nice. So we really got an x and an x squared, and x squared already counts that x factor. So I'm going to multiply the denominator by every term by x squared times x squared plus y squared. Clear the fraction. X squared times x squared plus y squared, x squared times x squared plus y squared, and x squared times x squared plus y squared. My screen jumped on me for some reason. So when we do that, the x squared plus y squareds are gone in the first. Whoops, I didn't want them to actually disappear. I just wanted to cross them off. The x squared plus y squareds are gone, so we have 1x squared times 2x plus 2y dy dx equals, and x is gone with an x, so we have x times x squared plus y squared plus the x squared is gone with the x squared. We have x dy dx minus y times x squared plus y squared. And we have to do a lot of multiplying before we can do any solving. So we'll just distribute the x squared through. Gives us 2x cubed plus 2x squared y dy dx equals, we don't really have to distribute the next one through. It doesn't hurt if we do it, though. X cubed plus xy squared. Plus, we've got to do some FOILing here. So we've got, distribute the x through. We got x cubed dy dx. Continuing to distribute the x dy dx gives us plus xy squared dy dx minus x squared y minus y cubed. And now we're ready to start solving. Let's get all the dy dx terms on the same side. I think it's going to be easier to move them all to the left this time. So I'm going to subtract x cubed dy dx, subtract xy squared dy dx. That moves them all to the left side. X cubed dy dx minus xy squared dy dx. We got to get rid of everything without a dy dx on the left, so we'll subtract 2x cubed from both sides. Line up the like term. We actually had one this time. And when we subtract, we now have 2x squared y dy dx minus x cubed dy dx minus xy squared dy dx equals, on the other side, 1 minus 2 is negative x cubed plus xy squared minus x squared y minus y cubed. And we now know that our next step is to factor out the dy dx. We don't care how ugly it is. Dy dx times 2x squared y minus x cubed minus xy squared is equal to negative x cubed plus xy squared minus x squared y minus y cubed. And one last step to finish it out. Divide by that factor so that dy dx is all alone, and the derivative is now equal to negative x cubed plus xy squared minus x squared y minus y cubed all over 2x squared y minus x cubed minus x y squared. I want to notice the pattern that we continue to use. We take the derivative of both sides of the function, no matter how ugly it gets, treating y like it's got x's inside it. So it's part of the products. It's part of the chain rules, which means that the derivative of y is dy dx. Every time we take the derivative of y, it's dy dx. And then solve for dy dx, which, no matter how ugly it gets, is the same every time. Get all the dy dx's on one side, everything without on the other side, so that we can factor out dy dx and divide. These take practice. Practice, practice, practice. Please look at the homework assignment before you come to class so you know what questions you have. Then tomorrow's video, we're going to take a look at how we can use these with what are called related rates. If you can master these, related rates are easy. If you don't take the time to master these now, related rates tomorrow are going to be very difficult. So please take the time to do this entire assignment. Struggle through it. Ask questions. We'll see you in class.